Hey everyone, good afternoon. Let's give it about 30 seconds here while we wait for people to come in. We got a good crowd already. Hope everyone's doing well. All right, Adam, you want to get started here? You ready? All right.
Ready.
All right, everyone. Thanks for joining and good afternoon. My name is Matthew Warren. I'm with Air Carolinas, located here in Columbia, South Carolina. I'm in the critical environments department, and we're excited to have Adam Donovan with us to share a little bit about Antrum. We've got a lot to cover, so we're going to dive right in. And I've got a brief little bio about Adam that I thought would just help kick us off here. So please join me in welcoming Adam Donovan, the founder and president of Antrum, a company based in Grand Rapids, Michigan, that is transforming how buildings manage ventilation through intelligent air monitoring. Adam holds a degree in electrical engineering from Grand Valley State University and has led multiple companies through periods of significant growth. Since founding Antrum in 2020, he has overseen the development of the groundbreaking platform, combining hardware and software that helps facility teams improve safety while optimizing energy efficiency. In addition to working at Antrum, Adam is actively involved in ASHRAE technical committees, contributing to the standards that shape healthier, more sustainable buildings. He's recognized not only for his technical leadership, but also for his commitment to people, prioritizing communication, team building, and talent development throughout his career. Outside of work, Adam is active in his church and enjoys coaching his 4 kids in various sports. Please help me welcome Adam Donovan. Adam, take it away.
All right. Thanks, Matt. Appreciate it. Thanks, everyone, for spending the lunch hour with us today. We have an action-packed agenda, so we'll get rolling right into it. We'll start with just a very high-level overview of demand control ventilation. Then we'll get into centralized sensing, Antrum's platform, and then why Antrum may make sense for some opportunities that you're working on. And then I will leave time for questions at the end. Matt, if you can do me a favor, maybe monitor the chat. I don't mind being interrupted, but if you could monitor the chat and interrupt me, that'd be great.
Yeah, feel free to put some comments or questions during the presentation. Makes it a little more interactive.
Yeah, for sure.
All right.
Okay, so just to kind of set the stage for demand control ventilation, I serve on a couple technical committees. You probably got that out of the little bio there, but I was in Phoenix in June, which ironically, I think the only place hotter in the country was Michigan at that time. But while we were there, the president of ASHRAE was encouraging all of us to become healthy indoor environmentalists. Many of you may have seen this in an ASHRAE journal article, but the theme for ASHRAE for the year is healthy buildings designing for life. So this doesn't necessarily have to be all granola girl stuff, and green focused, but you can see 40% of CO2 emissions are from the built environment, and well over half of that is from the HVAC systems that we're all obviously playing an integral role in each and every day. And I think the main thing that I'd like to connect for you is that the goal of decarbonizing buildings and also helping end users save energy are really the same thing, right? And so that's kind of how we set the stage for demand control ventilation, which is really nothing more than providing the right amount of airflow at the right time in the right location. And so there's a definition on the screen there, but really it's more around dynamic ventilation based on need as opposed to a static approach to ventilating different spaces. This is just a quick snippet from the Department of Energy saying just specific to CO2-based demand control ventilation, which I think many people are more familiar with. there are significant energy savings. And so we're not just talking about gyms and auditoriums. We're talking more like dynamic reset of minimum ventilation rate based on actual CO2 readings. And there's a 10 to 30% savings. I think there's a lot of reasons why most people don't believe that number, or maybe haven't experienced that number. Some of which are not even listed in the impacts here, right? It's more of how it's done. And so that's kind of what gets us to the next slide, which is the traditional approach to CO2-based demand control ventilation or sensing in general. The green dot represents a space-mounted sensor, a sensor on a wall. It's obviously very rudimentary, like floor layout, if you will. So just imagine a school or a commercial office building, and each green dot represents a sensor on the wall in each one of those zones. This is typically how it's done. Most people maybe don't realize that according to ASHRAE 62.1, each of these sensors has to be calibrated every 5 years if it's being used for demand control ventilation. Many of the clients we talk to, I think that's maybe the plan on day one, is to use the sensor for DCV, and it often gets programmed out for a variety of different reasons and becomes a binary, right? If it's over 1,500 parts per million of CO2, do this. Otherwise, behave as normal, almost like programmed out, if you will. One of the main reasons why at least a lot of the clients we talk to do not experience energy savings associated with CO2-based demand control ventilation. The kind of, question for the audience, and we don't have to sit here and wait for everybody to answer, but most of the clients we talk to, or most times if we're in an engineer's office or presenting to end users, very rarely do these sensors actually get calibrated. This is a study that you may have seen, is done quite some time ago. A decent number of sensors, different manufacturers, different ages, but all relatively new. And over 80% of them read high, and they were high, almost 40% on average. And so the takeaway there should be, if the sensors aren't calibrated, we end up over-ventilating the space, right? So that we're back into this emissions energy spend scenario. And so it is an opportunity to save energy and decrease emissions, or at least CO2 or carbon. So one of the reasons, or some of the major reasons why we end up getting here is, if you think about each one of those sensors in the individual locations, it'd be super labor intensive for the facilities team or even a service provider to go around to each of the zones and calibrate those sensors in the field. Those zones where the sensor is actually installed are usually occupied during the hours in which the facilities team or a service provider would be on site, which sort of makes them limitedly accessible, not regularly accessible. And that ultimately leads to a lack of maintenance, which then leads to sensor drift and unreliable data, which then leads to missed energy savings opportunities. So this is when we kind of pivot to centralized sensing a little bit around, why centralized sensing, what is centralized sensing? And so the idea with centralized sensing is to use one sensor. We call it a sensor pack, and that's this picture on the screen here. And what we have in each of the zones would be either a faceplate, as shown on the drawing here, or a duct probe. You'll see it later. I can show it in my screen, but it's a little 1-inch duct probe that goes into a duct. Usually that's used for the reference channel. But the goal here now is we've taken 16 individual discrete wall-mounted sensors, and we've boiled that down to one sensor. So if we're just talking CO2, one CO2 sensor serving 16 unique zones. So besides the drastic reduction in the amount of end devices, one of the biggest advantages would be, if you think about CO2-based DCV, and I think ASHRAE, I don't know if they've updated the number. I can't remember the latest version in the handbook. But at one point in time, they said to control CO2 in the indoor zones at 650 parts per million over outside. And even if it's not an ASHRAE recommendation, but it's just how you want to control the building, controlling based on a differential is highly advantageous when you're using centralized sensing, because although our sensor will drift and needs to be calibrated every 5 years as well, we're using the same sensor for our reference, outdoor air zone, as we are for the indoor zones that we're controlling. So the drift is the same between the zones, and you can maintain the constant differential. ultimately, this yields a much more accurate and reliable way of controlling based on, CO2, which is what we're talking about right now, but regardless of what you're sensing. And so the way Antrum X does this is a little bit different. We'll get to that, but this is essentially a screenshot of my panel. We'll get to the panel behind me in a minute. We make the panel in 3 different sizes, 1 physical size, 3 different sizes in the sense that we can monitor either 8, 16, or 32 zones. And so in a 32 zone, we have 2 sensor packs that are stacked on top of one another. So essentially, we like to say we're monitoring 32 zones from a single location, or 16 zones with a single sensor. And so some common applications for our technology and centralized sensing in general are CO2-based DCV in education, specifically in K-12. Centralized dew point monitoring for operating rooms and chill beam. I would say those are more, we seem to be applied more in those applications than the ones below, which are commercial office, IAQ monitoring, which we do some of, but then also VRF, refrigerant detection. So we do offer refrigerant sensors for the new refrigerants. We'll see how long those last. And it's less around ASHRAE standard 15 and more connected with the added expense to add a refrigerant sensor to an existing sensor pack. So if we're looking at a K through 12 facility that's interested in doing CO2-based DCV and it happens to be a VRF system, adding refrigerant to highlight where a leak might be so that we can find out about it not on a design day and essentially prolong the usable life of the mechanical equipment. That's the real value proposition for refrigerant detection with respect to Antrum. And then a lot of where we're applied, if you will, is in the lab space. So both on optimizing the stack velocity out of the exhaust fans, which is often referred to as chemical monitored exhaust, as well as optimizing the air change rates in the laboratory. There was just a question.
Yes. What do you do about different types of spaces reporting to common pack sensor, like an office and a classroom and a conference room? Different types of spaces reporting to one common pack of sensors.
Yeah, so that's the whole goal of the technology. So if the question, if I'm understanding this correctly, if the question is certain spaces are worried about certain things and others may not be, then as an example, if you had a sensor pack with CO2 and particles and TVOC to monitor for gases, you could just report on CO2 in the classrooms and the conference rooms, and then you could just report on the TVOCs and the particles in the labs or whatever, if I'm understanding that question correctly. But you can separate the sensors. Okay.
That's it?
Good.
Thanks, Adam.
Yep. So just kind of segueing into the critical environment. So ventilation is our primary means of both controlling airborne hazards, as well as, heating and cooling the space. And we waste as much as 50% of our HVAC energy on improper and inefficient airflow control. So getting this right is super important. It's super important because the value proposition for Antrum or centralized sensing in the critical environment is safety and energy savings. So the air change rate is obviously a big piece of that. And so how do we get to establishing the right air change rate? There's a lot of different ways to get there. There's not like a one size fits all model. You can see even from this, it's not the same number top to bottom from all the different codes or standards. Similarly, a lot of those codes and standards have been progressively endorsing what I would like to refer to as like a dynamic ventilation rate. If you read what's in green, it's speaking to more of a dynamic approach to ventilation as opposed to a static approach. And so at the end of the day,
why do you call it a dynamic approach there? What's the keywords that you're pulling from?
Yeah, demand control or demand control ventilation, demand-based control. Generally speaking, varying the amount of ventilation based on what's actually happening in the environment. So now we've kind of transitioned from CO2 only to the critical environment where we're looking at a lot more things than just carbon dioxide. still the same principle applies in terms of dynamically ventilating the space, as opposed to the traditional approach has been, 6 unoccupied and 12 occupied, and let it run 24/7, 365 that way.
Right.
So another common approach, and this is kind of a copy paste from a Smart Labs toolkit, is a ventilation effectiveness test. Oftentimes, if you're using data and science to establish the correct air change rate for your lab, a lot of life science and higher ed universities do this at least at one point. And that's how they come up with this quote unquote one size fits all static number that works for all their labs. One of the benefits Antrum can offer in terms of safety is we can sort of be this continuous ventilation effectiveness test. So we're continuously monitoring the air quality of the lab, comparing what's coming out of the lab to what's going into the lab. And so the goal here is to minimize the risk of exposure by detecting concentrations when the lab is unoccupied and when it's occupied, right? So that we can be sure that at the end of the day, we're controlling dosing or accumulation, or at the very least, maybe controlling is the wrong word, but preventing it, right? And our main means of preventing that is ventilation. So in this case, if you think about Antrum or sensing technology in a critical environment as it pertains to safety, oftentimes we can be used to increase ventilation, right? We can highlight when conditions are outside of design conditions with respect to different contaminants, and then increase ventilation. Now the inverse is true too. Inverse meaning our ability to optimize ventilation based on energy savings. This is a study that was done and published by I2SL that said, these labs are below contaminant thresholds essentially 99% of the time. ASHRAE did a similar study with respect to demand control ventilation in labs, saying that high flow is really only needed 2% of the time. So I think we're left with this idea of, well, how do we take advantage of the vast majority of time when we're clearly or potentially overventilating the space? It's a big deal in labs, as many of you know. It's once through air, right? And optimizing ventilation is a cascading impact. Not only are we saving on fan energy, but then we're also saving on heating and cooling energy. And so labs use 3 to 4 times the energy of a commercial office building. And the main lever for controlling emissions and cost reduction is optimizing ventilation. So now we'll get into exactly how Antrum works and how we do this, how we sample the air, and maybe what makes Antrum different than other centralized sensing solutions that you may or may not have experience with. So this is just another picture of the panel that gives you an idea of how the parts and pieces get connected. And so I'll run through this, and I will stop at the end of the how it works and just maybe pause to make sure everybody's on the same page. We have either a faceplate, this would be located in the breathing zone of a monitored zone, or a duct probe. In a lab setting, we're often using these duct probes, and they're located in the general exhaust. And then we're running 1/4-inch tubing. It's specific lab grade tubing for lab environments. It's standard 1/4-inch poly for non-lab environments. And we're running that tubing, we're home running it back to the panel. Okay, we have a guideline of 300 feet. For any of the engineers on the call, or even installers, commercial buildings are designed, believe it or not, the max network drop distance is 300 feet in a commercial office or a commercial building. So we're undoubtedly able to find, almost always able to find, an IT closet, a mechanical room, or electrical room where we can install our panel. And then due to the flexibility of the panel, the different sizes, we can get it somewhat centrally located to the zones we want to monitor, and then home run the tubing. Now, the way we pull air samples is pretty unique. We use we call it an air accelerator. I'm going to bring it up here. It is literally just a venturi. So it has 2 tapered cylinders, and then there's a low pressure point at the middle. And then essentially this is suction. So air is being pulled up to the air accelerator. And so the reason we have 2 of them, I'll kind of walk you through how this works, is we're pulling, if you follow my cursor, can you see my cursor, Matt? Yes. So if you follow my cursor, imagine we're in a zone that we're monitoring. We're pulling air through that faceplate or duct probe, through the 1/4-inch tubing into the panel. Now, let's say we're monitoring lab or classroom 100. That air sample, it comes into our panel. We have a manifold here. That if we're on lab or classroom 100, we're directing that airflow to the sensor pack. Okay, so that airflow is then drawn through the sensor pack. It's drawn up to the air accelerator. And then something different about our technology, every air sample that we pull is then dumped into the exhaust and exhausted out of the building when this air accelerator is connected to the exhaust. The reason for the second air accelerator is we have another outlet to our manifold, which allows us to essentially prime the next channel. So while we're pulling lab or classroom 100's air through the sensor pack, we're pulling lab or classroom 101 to our panel, and then we're just drawing out through the exhaust side of our manifold and then exhausting that air sample out of the building. And the reason we do that is it's analogous to like a hot water recirc pump. When we switch from lab or class 100 to 101, we already have 101's air physically present in the panel, and we don't have to wait for it to be pulled down the tube from up to 300 feet away. So that's the reason why we have two air accelerators. I'm going to get in the install, and then I'm going to go to a demo, and then I'm going to pause for questions. So this is a good one-line diagram, just kind of highlights our system architecture for anybody old enough to remember pneumatics. This is very much like a pneumatic install. So we have 2-inch tube that connects the air accelerators to the ductwork. We have 1/2-inch that connects the air accelerators to the panel. And then we have 1/4-inch that connects the monitored zones to the panel. We have a single 120 volt connection at the panel. We have a gateway, which is BACnet MSTP or IP. So that is a single connection at the panel. And then we have an optional internet connection, which I'll talk about in a minute here. This is a pictorial representation of what this might look like in a commercial building, where we have our panel in a mechanical room, the air accelerators connected to ductwork within 100 feet. Is typically what is the guideline for this 1/2-inch hose. And then we're running 1/4-inch tubing out to our monitored zones. You can see we're picking up in the general exhaust, and this is our supply air reference. So if I switch my camera, so now you should be able to.
I just switched it to spotlighting.
Okay.
For everyone.
Good. So you should be able to see the panel. Just kind of walk you through the.
Would you stop sharing your screen, please?
I'm sorry. Yep.
Yeah. There you go. Perfect. Thank you, sir.
Yep.
Awesome.
So now you can see the panel. My goal here is just to kind of familiarize everybody with the different parts and pieces so that we can connect how it works. You can see the air accelerators. Now remember, this is a demo, so we just have 2 pieces of ductwork. This is meant to be the supply. Then we have the air accelerators connected with the 2-inch hose between the supply and the exhaust. Okay. We have our 1/2-inch hose that's connecting to the side of the panel over here. And then we have 2 zones. We're just kind of highlighting 2 zones. One's the faceplate, the other's the duct probe, which is a little hard to see, but it's on the underside of the exhaust to kind of simulate where the general exhaust pickup might be in a lab, or even return CO2, if you will. And those air samples are being pulled into what we call our manifold. And so you can see there's a little indicator light that shows you which zone is active. That light means that zone's air is being sent to the sensor pack. Okay. This is our controller. So this is what's controlling the solenoids. These valves are the only moving part in our whole entire system. The operation of this valve is checked every single cycle. So if we're on a zone, before we switch to the next zone, we actually close that valve. We have a velocity sensor in our sensor pack, and we verify that the valve fully closed and that we're not able to get any airflow. That's how we verify the only moving part in our system is continuously operational. If it's not, all of our BACnet points carry a reliability flag and have some text associated with it. So we would highlight a valve failure in the event of a valve failure. We have installs going back to 2011. These things are rated for 20 plus years of install based on the number of ticks, and we do not have a failure yet. Okay, so that's the manifold, the controller, our sensor pack. Okay, it's important to note that all of the sensors in our, all the available sensors are packaged in the one sensor pack. So I will have to jump back into the presentation and I'll show you the available sensors, but a typical vivarium sensor pack, so animal laboratory, would have a CO sensor, a CO2 sensor, two TVOC sensors, one that's more broad in its response and much more responsive at lower concentrations. The other one is much more responsive to methanol-based gases. We'd have a particle sensor, and then we'd also have an ammonia sensor. So one of the different differentiators for Antrum is we do have some dedicated VOC sensing. We sense formaldehyde, which is helpful for weld buildings, lead points, but also anatomy labs. And we have ammonia sensing, which is very helpful for vivariums. You can differentiate if you use the TVOC sensors and our ammonia sensor, you can differentiate between somebody cleaning a vivarium with isopropyl alcohol, which will excite the VOC sensors, but not the ammonia sensor. And then obviously having the dedicated ammonia sensor kind of adds that level of transparency. So all of the sensors are packaged in the one device. Our electrical components are in the lower right hand or left hand corner. Hopefully that's directionally accurate based on how you're looking at it. And then our gateway is in the lower right hand corner, BACnet MSTP on the side, BACnet IP below, which we're connected to right now. And then we have a software platform, which you can see a glimpse of on the screen here. I have some slides to show you, to kind of show you a little bit more detail. This is a demo platform. It's not necessarily connected to the panel, if you will, but the software platform is a ventilation-based dashboard that highlights the amount of time all the monitored zones are at low demand or high demand. So it's a safety ventilation dashboard and also tracks energy savings by zone. And one of the more unique things about our technology is how simple it is to maintain, because we only have one moving part, but the only part that requires maintenance is our sensor pack, and it requires calibration. So we don't have mandatory subscription services. The way that we sell our calibration is we sell it at a fixed dollar amount so that end users understand exactly how much the ongoing expense of Antrum is. It's $1,444. And the rate at which you experience that expense or the frequency is dependent on the calibration frequency, which is dependent upon the application. If it's CO2-based ECV, it's every 5 years. If it's a lab with a TVOC sensor or an ammonia sensor, those two sensors have a 6-month calibration frequency. So you would experience that expense every 6 months. But this was really designed with the end user in mind. So you do not have to use, if you want to use Air Carolinas because they're your favorite service provider, have at it. If there's another service provider, or if you want to do it yourself, you have that flexibility. You're not locked in. And it was designed with the end user in mind because you can very easily do it yourself. So I'm going to turn the panel off and do a quick swap of the sensor pack so that everybody understands how much maintenance is involved with keeping this system updated. So you have 3 connections, no tools are required. One's a push to connect fitting on the left side. The other is a push to connect fitting on the right side. I can just slide in on a piece of DIN rail. There's a spring-loaded clip on the back and I just pop it off. And then there's a little M8 electrical connection. And so now I've essentially removed the sensor pack. Our calibration procedure is a replacement procedure. So we send you a new sensor pack with freshly calibrated sensors using NIST traceable instruments and gases. And so you'll get that with pre-postage for the sensor pack that you just took out to go in that box and get shipped back to Antrum. You take the sensor pack that we just shipped to you and you put it back in the panel. I always like to connect the electrical connection first. I think it's easier. And then I mount it on the DIN rail. Connect the tubing on the left. And then slide it to connect the tubing on the right. Turn the panel back on and you're good to go.
That's got to be the world's easiest calibration, right? That's pretty slick. Would you explain, Adam, real quick about what happens when some of the more complicated systems don't actually calibrate and they end up reading, positive? You get all kinds of false positives all the time, right? And how that that impacts
Yeah.
the customer and their faith in the system.
Yeah, so if you don't calibrate, I want to go back. Let me switch cameras here. There we go. And then I want to get back to presenting. If you don't calibrate, the sensors will drift quite drastically over a 6-month period of time, depending on the lab application that they're installed in. So if you don't calibrate, you do end up, it's like a CO2 sensor that's never calibrated. And I bet most people on this call know what that looks like, right? That's why they get programmed out. That issue is only exacerbated when you add more complicated and sophisticated sensing technology, like what we offer in the critical environment sector. So yeah, false positives, all sorts of alarms, whatever the case may be. The way our system works, you have lots of options over how to calibrate it. I guess the option you don't have is whether or not to calibrate it. If you don't calibrate it, our system will default to a high ventilation state. So I suppose you still have an option. The option is that you're just no longer going to use the data. And so our calibration timer is a backnet point. It's also available on our software platform. So there is a countdown. So you'll be notified either through Antrum, our software platform, or through your backnet. And ultimately, that allows you to manage your system. We're also very happy to manage the system for you, should you want us to do that, or another service provider. Again, you have options, but if you don't maintain it or you don't calibrate the sensor packs, we'll stop providing data once the calibration expires, so that we don't run the risk of, just like worst possible thing, right? Like you're at least in high ventilation state, and then you're in full control.
There's 2 questions in the chat here. One about, do you offer the remote monitoring and notification services? I think you mentioned that just a minute ago, or starting to go down that path. And if you're going to cover it later, we can cover it later. But
yeah, the quick answer is yes. In order to do that, you have to connect your panel to the internet. Our software platform is available over the internet. It's actually, the program is, we call it Antrum, is physically installed on the gateway in our panel. So if you connect the gateway to the internet, you can access the software platform on antrumi.com. That gives us the ability to do remote monitoring, diagnostics, and all that kind of stuff. If you don't, you still have access to the dashboard, whether it's hardwired from a laptop or a local area connection. You just got to type in an IP address. What was the other question?
Yeah, price. It says, how does your price point compare to Air Acuity Sensor Suite?
Yeah, yeah. It's I do have a total life cycle cost analysis in a minute here that compares them. They're listed as other, not by name, but I would say roughly 50%. It's quite a bit more cost effective, both initially as well as ongoing. So initially, you've hopefully by now, I guess now would be the time to ask the questions about how the system works, but hopefully by now you understand how the system works. We have a lot less moving parts and pieces. And so that savings, if you will, is passed on to the end user. Our goal is to become a staple of design, not to get one out of every 10 or 20 projects and be value engineered before the project even gets legs. And so when we developed the technology, we had that in mind, and we treated a space-mounted CO2 sensor as the competitor more than Air Acuity as it pertained to developing the technology and the price point. So hopefully that answers the question. I'll have another slide that adds some more dollars, hard figures to that. I don't know, there's probably not much else to talk about on the sensor pack. I do, because we're talking about that, we'll go to the next slide, since we're on the topic of installation. So we do offer retrofit installations. I think the other centralized sensing cat is out of the bag, if you will. But if you're familiar with this system, you know there's, we're going to call them valve boxes. They call them something else. But the equivalent to our manifold is separated into 4 valves and located throughout a facility, typically above the ceiling tile in hallways, sometimes actually in the mechanical room where the panel itself is located. One of the benefits of retrofitting that system with Antrum is for sure cost, flexibility, I would say complexity, like a much simpler system and therefore, much less expense. And our ability to do that just hinges on, I guess one of the benefits of that is you don't actually have to enter the monitored zones. So we can remove the valve box, cut their tubing, and then use a connector as shown in figure 3 to connect, their tubing from the zone to our tubing, which is then ran back to the panel. And so it's a relatively easy retrofit installation. There is an ROI associated with this because I shared the ongoing expense of $1,444, and that's a fraction of the cost of their assurance program. So that's an opportunity. Okay.
That's one reason why we're excited about it, is because there's not only from the initial cost, but the ongoing, there's a lot less moving parts, a lot less things that go wrong and fail. And that's why the price point that was mentioned in the comments, that's why it's a half, 50%, but they continue on, Adam. It's great.
Yeah. Yep. Okay. So now just kind of why Antrum, highlight some customers who've chosen to work with us. Most of the clients listed on the page here are, there are some CO2 based DCV applications like Apple. Chanel was a commercial office building with IAQ monitoring. There was a clean room application here in Grand Rapids. Most of the rest of them are labs and vivariums. And then there's some other like life science companies on this screen. I wouldn't say you want to do business with us because other people have. I think it's just helpful because the company is relatively new to highlight the fact that anybody on this call, should you have an application, it's not even close to our first time doing it. So with that understanding, this is the life cycle cost analysis that was done by a third-party MEP firm on behalf of an R1 university. So they were contracted to essentially evaluate, does DCV make any sense at all for us? And could you evaluate the DCV options that we have? We talked about who other is. Obviously, Antrum's listed as sensor packs. And then they looked at a couple different discrete sensing technologies. Thankfully, Antrum came out in a very positive light on this study, and the MEP firm was willing to share the information with us. I believe the total cost of ownership or life cycle analysis was done over a 20-year period of time. We are now basis to design on 3 different performance energy contracts with this particular university. So pretty exciting for us. The other reason why Antrum is we do highlight our value proposition, and that is not predicated on or dependent on you connecting your panel to the internet. You get our value proposition front and center, whether the panel is connected to the internet or not, as long as you obviously commit to accessing Antrum I. And so we developed a software platform that is, we call it a ventilation platform, really. It's how you set up our system. Our gateways and everything come fully programmed. But if you want to modify thresholds, like contaminant thresholds, you have the ability to do that in Antrum I. So there's some Antrum setup, configuration, or modification of the system, if you will, that you have the ability to do. But we also highlight that 98% speaks to all the zones that we're monitoring and the amount of time that those zones are at low demand. Okay, so we highlight the amount of time you're at low demand and high demand. And then we also highlight key metrics on a zone by zone basis. We highlight the amount of kilowatt hours that you've reduced, both by the building and at the zone level. And then we equate that to metric tons of CO2. This picture is showing pounds of coal, but the standard view is metric tons of CO2. So the screen that I'm on now would be equivalent if we clicked like room 107 or one of the rooms on the list there. It takes us to a room level dashboard. And so this is it's a bit of a garbage in, garbage out system. This dashboard is no added expense to the end user. You have the ability to map backnet points to our system. You can map as many backnet points as you want to our system and get the real-time value of those points. So as you're mapping SASH sensors and thermostats and general exhaust valves and supply valves and fume hood exhaust valves, all of the things that speak to what's happening from a ventilation standpoint. And this is really focused on critical environment, but we have the same sort of thing that's set up for CO2 basis, just much less complex. All of that information can be mapped to our platform. Now, if you want to trend the data, so you can trend all of the air quality data that Antrum's generating for the life of the hardware at no additional cost. If you want to trend the data that you're sending to our system over BACnet, which would ultimately probably be trended at the BMS level. If you also wanted to trend it on Antrum I, we would have to upgrade your license. It's a one-time fee. It's a couple $1,000s based on the number of points that you want to add to the system. So it's not a recurring expense. It's just a one-time fee to get the dashboard set up. But we allow you to map as many points as you want and see the real-time values and essentially experience the benefits of the platform without committing any more financial resources than you already have. And so this is the zone level dashboard. And then we also, if you click the reduced emissions card, it takes you to the amount of, it highlights the amount of time you're at low demand, and then it breaks down the kilowatt hours reduced based on conditioning and fan energy. And then there's different set points in there, like we use an outside air temperature sensor that you have on site, or if your panel's connected to the internet, we use local weather data and your set point that you have for control. And then we have efficiencies that you can modify on Antrum I for like how efficient is your system for heating and cooling and such. What's the efficiency of your fan? And so the more information you send us, the more accurate our energy savings calculation can be. Yeah, Matt.
Quick question in the chat. It's about the tubing. Is the 1/4-inch tubing plenum rated?
It is. The 1/4-inch tubing is plenum rated, and it's chemically inert. So one of the main things in particular with critical environments is you want to prevent against adsorption and absorption, essentially particles being absorbed into the material and gases sticking to the material. And so the lab grade tubing that we use, which is fluorinated polymer, is specifically formulated for to protect against these phenomena. There's another question, I think.
It was there, but I think it got deleted. Or maybe it'll come back. I don't know where it went. Yeah.
Okay. I thought it was something about install. So we're kind of nearing the end here. I want to highlight some of the differences, differentiators, if you will, with respect to Antrum's technology. So one of the things with centralized sensing is the concept of shared tubing. And so the way Antrum's system is developed, the amount of tubing that is shared in our system is very minimal. I'm actually going to pan back to my camera here and highlight this for you. Can you see that, or should I stop sharing?
Yeah, just stop sharing and I'll make it spotlighted.
Okay. So if you notice on the, somebody's asking a question about the farm. If you notice on the left side of the sensor pack, in terms of cross-contamination, this tube and this sensor pack is the only shared volume in the whole entire system. So we talked about the other system that has valves located throughout the building. There's a lot of shared volume. The amount of shared volume is dependent on the installation. Documentation of that installation is very critical because it determines purge time. Cross-contamination should be a concern if you're using centralized sensing, in particular in the critical environment. And the way we deal with that is, like I mentioned earlier on how we test the valves with our velocity sensor. We have a known volume. We do final assembly of all of our panels in our UL panel shop here in Grand Rapids, Michigan. Our engineers designed all the hardware and software in this panel. So we know the volume in the sensor pack and obviously in the tube. That's something that we're controlling at our factory. We have a velocity sensor in our sensor pack, so we know the volume and we know the speed at which the air is traveling. And we know that speed can vary from zone to zone, which means our purge time will vary from zone to zone. But it also means we know exactly how long we need to spend purging any zone before we move to the next one. So we can be sure that we're reporting on the correct zone's data. And that's one of the biggest differences for how we do centralized sensing by minimizing cross-contamination. I'm going to switch back now. Did somebody have a suggestion on the PowerPoint?
They're asking, could the PowerPoint be made available?
Oh, yeah, absolutely.
Slides. Okay. And also, this will be on our HVAC TV podcast that Tony Mormino does, as well as we're going to have the video recording that we'll send out to the folks that attended that you could share with your team as well. All right, back to you, Adam.
Okay, yep, along the lines of safety, because we're not using mechanical pumps, which would essentially exhaust all the air samples in the room in which they're located, every air sample that we pull with our system is exhausted out of the building. I mentioned our installation is a single 120 volt connection. It's a very, very low power application. Very simple to install from an electrician standpoint. We have a single moving part, which is the valve, which we talked about. No mechanical pumps, right? One of the biggest reasons we're able to offer our technology at the price and the maintenance, the way that we're able to accomplish that at such a cost-effective price is because we just don't have all the moving parts. We don't have that many failure points. And then the toolless calibration. So just to kind of comment on that again, there is no mandatory subscription. We'll happily, the more we calibrate sensor packs for end users, oftentimes they end up using a service provider, or they end up asking us for some price agreement over some fixed period of time. Happy to have that conversation, happy to get people on contracts, happy to work with their favorite service providers or with end users. Our goal is to control at least the ongoing expense of the Antrum system, because from our perspective, if I sell a system to your facility today, I'm going to change your baseline energy spend. If you integrate it and use our data to optimize ventilation, I'm going to change your baseline energy spend. In 5 years from now, if you still happen to be at that facility, you have a new baseline. It's super important that I'm able to offer the technology at a price point that still makes sense based on the energy savings that you're still experiencing, even though it may not feel like it because you have this whole new baseline. And so that our method or strategy of providing this flexible solution so that end users have choices is so that in hopes they will continue to maintain the system and calibrate the sensor packs. Scalability. So I talked about some of our dedicated sensing, which is something that's not offered in the marketplace, both formaldehyde and ammonia. But we also have scalability. There's actually a project in the Carolinas in your area right now where there's a CO2 panel that's being used for CO2-based DCV on the office and conference room side of the facility. And then there is a lab panel, and the lab panel is being designed as a lab panel, but with a CO2 only sensor pack. And the reason is because the end user wants to get information, and then we could very easily upgrade the sensors in the future and include particle sensors and TVOC sensors. And so there is ease of scalability. We don't have to go into all these individual rooms, right? We go into the one mechanical room where our panel is located, and we swap out the sensor pack. Very, very simple. And the value, right? We're still on the why Antrum page. A big reason why is the value. Very attractive initial and ongoing expense. And the last thing I would say before we stop and ask for questions, looks like we have about 10 minutes left. I have hopefully a funny little clip to leave you with. I think that DCV over the years, whether it's space mounted or other centralized sensing solutions, has found a way to be this complicated thing, and it doesn't really need to be. And so that's one of the major things we feel we solved here at Antrum. So I'll play this for you.
I love that. That was great.
Yeah. So those of you that did your homework, there's couple more videos like that on our website. We have a lot more information, but I appreciate you guys spending time, and I'm happy to spend the next 10 minutes or so answering any questions you may have.
And while we're opening it up for questions, please put your question in the chat. Could you just talk a minute? I know we talked yesterday with Fran, Adam, about what's involved with some of the other systems out there when it comes to the calibration and all the different moving parts and modes of failure, as opposed to the streamlined system that you guys have come up with.
Yeah, so the other centralized sensing solution would have multiple, think of it like a server rack, would have multiple PCBs, printed circuit boards. One might monitor CO2 and CO. The other circuit board might have particles and TVOCs, and then there's oftentimes a third one for lab applications. And so each of those has to be removed individually. There's multiple electrical and pneumatic connections on each one of those. It has to be done by a factory authorized representative. My understanding is there's a specific order of operations to both the removal and then reinstallation of the freshly calibrated sensors suites. And so that's a big part of it. And then there's a once it's installed, then you have to do this vacuum decay test, which essentially is the one-time test of the valve functionality. If a valve happens to fail, you then have to take, an X foot ladder around an occupied facility and try to locate where the valve boxes are, and then try to diagnose which valve is actually a problem. And there could be up to 16 valves, 32 valves on a single panel that are scattered throughout the facility, and there's no feedback on which valve box has the valve failure. So a lot of this is covered by the assurance program. So like if you're an end user on this call, you may not know that any of that's going on, but that's what the factory authorized representative is doing when they're charging you, $10,000+ a year to maintain the system. So it's a drastically different setup. So you could argue that there's a downside to home running the tubing on the Antrum installation, right? Like, oh, it's more difficult from an install standpoint. I have to home run the tubing throughout the facility. We tried to kind of counteract that with offering the panel at different sizes, which you can then minimize the length of tubing that you're pulling. But the benefit for locating the valves in the panel, in our minds, after doing some market research, just completely outweighed the benefit of locating them outside of the panel, or the headache associated with doing it that way. So hopefully that answers the question, Matt.
Yeah, that's great. A lot less headaches, a lot less cost.
Yeah.
A lot smoother, simpler. Any other questions before we wrap it up here? We appreciate everybody being on. All right, this video will be made available in the Teams meeting, but we'll also share the link with you once we get it posted, and we'll get it on the HVAC TV podcast that Tony Mormino does. And thank you, everybody. Adam, thanks so much. Thanks so much for joining.
Yeah, thank you, guys.
All right, everybody. Have a great day.
Thank you.